The natural numbers count perfectly well, until subtraction asks for an answer that is not there. We will construct the integers from ordered pairs of natural numbers. Then verify that the resulting arithmetic is actually well defined. Because writing the minus sign is easy, earning the right to use it is where mathematics keeps the receipts. In the natural numbers, 3 minus 5 is not defined as a natural number. We want a new number solving x plus 5 equals 3, while preserving the arithmetic we already trust. So we must specify the new objects, decide when two of them are equal, and define every operation without depending on arbitrary notation. Start with ordered pairs of natural numbers. The pair 5, 3 is intended to behave like 2. The pair 8, 6 should describe the same integer, while 3, 5 should describe -2. We may think of the pair a, b as the formal difference a minus b, but that is motivation, not a definition. Our raw objects are simply elements of the Cartesian product of the natural numbers with themselves. Declare a, b equivalent to c, d exactly when a plus d equals b plus c. For 5, 3 and 8, 6, both cross sums equal 11, so the pairs are equivalent. 0, 2 and 3, 5 also match, while 5, 3 and 3, 5 do not. Cross addition captures equality of formal differences using only addition in the natural numbers. Reflexivity follows from commutativity of natural number addition. A plus b equals b plus a. Symmetry is the same equality read in the opposite direction and reordered. For transitivity, assume the first pair is equivalent to the second and the second to the third. Add the two equalities and cancel the common natural number terms c and d. The result is a plus f equals b plus e. Thus the relation is reflexive, symmetric, and transitive. The quotient machinery may now enter without setting off an alarm. Define the integers to be the quotient of the set of natural number pairs by this equivalence relation. The notation bracket a, b means the entire equivalence class containing the pair a, b. Two bracketed pairs are equal precisely when their representatives are equivalent. The pair is only a representative. Calling it the integer would preserve duplicates and defeat the construction with admirable efficiency. Define addition by adding the first coordinates and adding the second coordinates. For example, bracket 5, 3 plus bracket 1, 4 becomes bracket 6, 7. The intended formal differences are 2 and -3, whose sum is -1. And bracket 6, 7 indeed represents -1. A promising coincidence. But examples do not establish well-definedness. Suppose both input classes are written with different representatives. The two displayed equalities express the corresponding equivalences. To prove the two proposed sums equivalent, we must establish this cross-sum equality. Rearrange the left side using associativity and commutativity in the natural numbers. Replace a plus b prime and c plus d prime using the assumptions, then rearrange again. Therefore addition gives the same integer for every choice of representatives. It has earned the adjective well-defined. The mnemonic expansion of a minus b times c minus d separates positive and negative contributions. Accordingly, define the product as bracket ac plus bd. AD plus BC. The definition itself uses no integer subtraction. For bracket 5, 3 times bracket 1, 4. The result is bracket 17, 23, representing -6. Now comes the algebra usually hidden behind the phrase. One checks that this is well defined. First hold the second factor fixed, and replace bracket a, b by an equivalent representative bracket a prime. B prime. Multiply the equivalence equality by circa distributivity gives the first displayed identity. Multiply the same equality by D to obtain the second identity. Add and rearrange those identities. The cross sums of the two proposed product pairs are equal. Therefore, replacing the first representative does not change the product class. Let P denote the displayed pair product formula. We proved that replacing its first input preserves equivalence. The formula is symmetric in its two pair inputs. By commutativity of natural number addition and multiplication. So the same lemma replaces the second input as well. Replace the first representative, then the second, and use transitivity of equivalence. Multiplication is therefore well defined on equivalence classes. That brief check has now been expanded into the check it actually was. Define integer 0 as bracket 0, 0, and integer 1 as bracket 1, 0. Define the negative of bracket a, b by swapping the coordinates. If two original representatives are equivalent, the swapped representatives satisfy exactly the reversed cross-sum equality. Adding an integer to its negative produces bracket a plus b, b plus a. Those coordinates are equal, so the class is integer 0. Additive inverses now exist by construction. Map each natural number n to the integer class bracket n, 0. Call this map iota. It is injective, because equality of bracket n, 0 and bracket m, 0 forces n equals m. The map preserves addition and multiplication directly from the definitions. We may therefore identify n with bracket n, 0, and negative n with bracket 0, n, without corrupting natural arithmetic. Natural number trichotomy gives exactly three possibilities for the coordinates of any representative. If a equals b, the class is 0. If b is less than a, there is a unique positive n with a equals b plus n. And the class equals bracket n, 0. If a is less than b, there is a unique positive n with b equals a plus n. And the class equals bracket 0, n. Thus every integer is uniquely 0. A positive natural number, or the negative of a positive natural number. Define x less than or equal to y when y equals x plus the embedded image of some natural number. This definition uses only integer classes and well-defined addition, so it is automatically independent of representatives. For pair representatives, the condition is equivalent to a plus d being at most b plus c. Indeed, y equals x plus iota of n exactly when bracket c, d equals bracket a plus n, b. The equivalence relation changes that class equality into c plus b equals d plus a plus n, which is precisely the natural number inequality. The construction is complete, but familiar integer laws still require proofs from the definitions. Commutativity, associativity, and distributivity follow from natural number laws, but only after representative calculations are checked. The order laws, trichotomy, and absence of zero divisors also need arguments. They are not difficult, but repeating every proof would turn a real analysis prelude into an abstract algebra residency program. So we record the obligations and leave their routine verification outside this video. We began with pairs of natural numbers and imposed the cross-addition equivalence relation. The integers are the resulting equivalence classes, not the individual pairs. We defined addition, multiplication, and negation, and proved that each is independent of representatives. The natural numbers embed faithfully. Every integer has a unique sign and magnitude, and the order extends the natural order. That is the integer construction. Subtraction was not assumed. but additive inverses emerged from equivalence classes of formal differences.